Bismillahirrahmanirrahim. Assalamu alaikum and welcome to another lecture on tool and die design. Today we are going to start module 4, that is design of fits and gauges. I have divided this module into 3 lectures. In first lecture we will discuss limits and fits. So in this lecture we will focus on the basics of limits and fits, and you should be able to understand the concept and purpose of limits and tolerance. So this is the basic concept in the design of fits as well as in the design of limit gauges. You should be able to understand the concept of fits and related terminology like nominal size, basic size, allowance, clearance, and interference. We should be able to differentiate between 3 general types of fits: clearance, transition, and interference fits and their application. And we will primarily focus on the design of clearance and interference fits in this lecture. You should be able to understand the difference and use of basic hole and basic shaft system. You should be able to design different types of fits using NZ B4.1 recommendations. So this standard is based on basic hole system and uses unilateral tolerances. So you should be able to use this standard to design different types of fits. And finally, you should be able to interpret a design fit based on allowances. So once we have designed a fit, you should be able to make a sketch of it, and you should be able to explain what do the tolerances applied to a fit uh, practically mean, and what will be the practical implications of the tolerances that have been applied. So first we will discuss basic terminology, and the most important concept is the concept of limits. So it is impossible to machine a part to exact size. So we apply limits to the size of a part. Now limits are actually the allowed variation in either one or two directions to the size of the part. Limits are used to ensure proper functioning of the part. So limits are applied in such a way that the functioning of the part is not affected. So it is quite tricky sometimes to decide both the size of limits as well as the direction in which we are applying limits. So we will discuss this point in detail in one of the following slides. So limits are the maximum and minimum permissible sizes. So examples are shown in figures. So another important term that is related to limits is the concept of tolerance. So tolerance is the total allowable difference from a size. Total allowable difference from a size. So tolerance is the difference between the limits of size. So let's see some examples. So in this case, we are having a size of 1.000 plus minus 0.002. So the size from which we are applying limits is called basic size. So basic size is the size to which limits are applied. You can say this is the ideal size that we will focus to achieve. Now the variation in this basic size is allowed in both directions. So plus minus 0.002 means that we can have a size of 1.002, and that is called the upper limit of the size, and we can have a size of 0.998. So that is the lower limit of size. And the difference of these two, in this case 0.004, is the tolerance. So the type of tolerance that we are applying in this case is bilateral, because variation in both directions of the basic size is permissible. In this case, we are having a size of 1.500 plus 0.003 minus 0.001. So 1.503 is the upper limit, and lower limit will be equal to 1.499 because we are having a size of 1.500 plus 0.003 minus 0.001. So the lower limit will be 1.499 and the difference of the two here is 0.004 as well. So that is the tolerance. Now the difference in both cases is that here the tolerance is bilateral as well as equal. So amount of variations allowed from the basic size is equal in both directions. But here the tolerance is bilateral, but it is not equal. It is bilateral and unequal. So on the upper side from the basic size, this is the basic size of 1.500. So on the upper side of the basic size, a variation of 0.003 is allowed, and on the lower side, a variation of 0.001 is allowed. So the tolerance is bilateral, but it is unequal. And in this case, in the case of a whole, the size is 1.000 plus 0.004 minus 0.000. So 1.004 is the upper limit and the lower limit is 1.000. And the tolerance is 0.004 as well. But here the tolerance is unilateral. The variation from the basic size is allowed in the upper direction only, and it is not allowed in the on the lower side. So that is example of unilateral tolerance. And that type of tolerance is actually very common in design. And you could notice here that the lower limit of 1.002 is equal to the basic size. So basic size and the lower limit are equal in this case. Now in all these three cases, we showed the upper and lower limits applied to the basic size. We can show the upper and lower limits only without actually mentioning the basic size. So in the case of a external feature like a shaft, the upper limit is shown at top and below that is shown the lower limit. So in this case, upper limit is 1.004, the lower limit is 1.000. And there is a horizontal line between the two. In the case of hole, it is just the opposite. So lower limit is shown at the top and upper limit is shown at the bottom. It was opposite in the case of a shaft or any external feature. So this is the basic concept of limits and tolerance. And this basic concept is applied to the design of fits as well as to the design of limit gauges. But the basic question actually that we will be answering in the design of fits and gauges is not only the size of limits, but the direction in which the variation in the size is allowed. So let's define what is a fit. Fit is the general term used to signify the range of tightness that may result from the application of a specific combination of allowances and tolerances in the design of mating parts. So the concept of fit relates to the degree of tightness between two mating parts. We will see how we can design different types of fits as we will move. Some more terminology. So dimension is a geometric characteristic such as diameter, length, angle, or center distance. And size is a designation of magnitude. So when a value is assigned to a dimension, it is referred to as size of that dimension. So diameter is a dimension. So if we are having a diameter of 2.00, that will be the size of that diameter. Nominal size is a size number used to identify the physical size of a part in general terms. An example would simply be 1.5 inches or 2 inches or 3 feet, for example. Basic size is the exact size from which the limits are figured considering the allowances and tolerances. So it is the ideal dimension. Ideal dimension which is desired if it were possible to machine without tolerances. So this is the size that we target. An example would be the nominal size of 1.5 inches written as 1.500 inches when applied to meeting parts. Allowance is a difference in dimensions prescribed to secure various classes of fits between different parts. It deals with positive allowance when there is minimum clearance and with negative allowance when there is a maximum interference between meeting parts. So actually the first part of the sentence is roughly defining clearance fits, and the second part of this sentence is roughly defining the interference fits. And we will come back to this definition in detail when we will solve examples of different types of fits. So both conditions are shown in the figure. If the nominal size is 1.5 inches, the basic size is 1.500 inches. The interference allowance in this example shown below is 0.002, and the clearance allowance is 0.004 inches. So we are having a shaft and a hole. The shaft has a diameter of 1.496, hole has a diameter of 1.500. So you could see that shaft is smaller than the hole. And we are actually discussing, and we will focus on the basic hole system in our this series of segments. So as we are having a nominal size of 1.500, a basic size of 1.500, so that is actually the size of the hole. And then we apply tolerances to the shaft in such a way that we achieve the clearance fit. So the shaft is smaller than the hole, and there is a gap of 0.004, so that gap is called clearance allowance. So this shaft can move inside this bush. On the other side, again, in basic hole system, 1.500 will be the diameter of the hole, and we will apply limits to the shaft if we are going to achieve an interference fit. So size of the shaft will be greater than the hole. So in this case, there is a negative clearance of minus 0.002, and we call it interference. So interference allowance is 0.002. Shaft is slightly larger than the hole, so we have to press it into the hole to achieve interference fit, or to actually assemble our two parts together. So in simple words, in clearance fits, shaft will always be smaller than the hole, and in interference fits, shaft will always be larger than the hole. And this difference in the sizes, if that is positive, that is called clearance allowance. And if that difference is negative, that is the shaft is greater than the hole, and that is called interference allowance. Now, there are two types of tolerances, as we have already seen. So the term unilateral tolerance means that the total tolerance as related to a basic dimension is in one direction only. For example, if the basic dimensions were 1 inches and the tolerance were expressed as 1.000 minus 0.002, or as 1.000 plus 0.002, these would be unilateral tolerances, because the total tolerance in each is in one direction. So we have seen this example already. So 1.000 is the basic size plus 0.004 minus 0.000. So this is unilateral tolerance. And of course, upper limit will be 1.004, the lower limit will be 1.000. A bilateral tolerance is a tolerance in which variation is permitted in both directions from the basic size, partly plus and partly minus. And as we have seen already, that this tolerance can be equal and it can be unequal. So an example of equal is the one shown here. So this is basically 1.000 plus minus 0.001. So it is written in this way for the sake of clarity. So it is an example of Bilateral tolerance because the total tolerance is 0.002 and it is given in both directions from the basic size, that is in plus direction as well as in minus direction. Now the basic question is this question, and this is the central question to the design of fates, gauges, and many other mating parts. And the question is when to use unilateral and when to use bilateral tolerances. This is the key question whenever you are designing two mating parts. So classical examples, actually the examples that we will discuss are the fits and gauges. So what is the answer to this basic question? So the general answer is that according to common practice, tolerances are applied in such a way as to show the permissible amount of dimensional variation in the direction that is less dangerous. So we are allowing variation in size. So we will allow variation in size in the direction in which uh, allowing the variation is less dangerous. So when a variation in either direction is equally dangerous, then bilateral tolerance should be given. And when a variation in one direction is more dangerous than a variation in another, then a unilateral tolerance should be given in the less dangerous direction. So on mating surfaces, with few exceptions, the tolerance should be unilateral. So that is a basic rule of thumb, basic conclusion. On mating surfaces, with few exceptions, the tolerance should be unilateral. And the two examples actually that we are going to discuss of mating surfaces, as I have repeatedly mentioned, are fits and limit gauges, because we are actually sort of joining two parts together in a way. So in such cases, the tolerance will be unilateral. So that is why the basic whole system that we will be using will be having unilateral tolerances, and similarly the standard that we will be using for the design of limit gauges will also be using unilateral tolerances. So where tolerances are required on the distances between holes. So this is an example of applying bilateral tolerances. So where tolerances are required on the distances between holes, usually they should be bilateral, as variation in either direction is normally equally dangerous. So if the distance between the hole is more than required, so for example, we are talking about the two holes in the part that have to be located using two pins in the body of the jig, as we saw in the case of jigs and fixtures. Now, if their distance is either smaller than required or either greater than required, so the holes will not fit into the pins. So it is equally dangerous if the distance increases or if the distance decreases. So in this case, we apply bilateral tolerance. The variation in the distance between shaft carrying gears, however, should have unilateral tolerance, and that should be in the positive direction. Otherwise, the gears might run too tight. So a slight increase in the backlash between gears is seldom of much importance. A slight increase in the backlash will still not affect the working of the gears, but if that distance is smaller than required, then the gears may jam and they may not be actually perform the primary function of rotation. So in this case, it should be a unilateral tolerance and given in the plus direction. And finally, another important concept related to the concept of limits and tolerance is material conditions. So we are having maximum material condition. A maximum material condition is that limit of size that provides the maximum amount of material for the part. Normally, it is the maximum limit of size of an external dimension and minimum limit of size of an internal dimension. And we will see an example on the next slide. Least material condition, a minimum material condition is that limit of the size that provides the minimum amount of material for the part. So normally it is the minimum limit of size for an external dimension and maximum limit of size for an internal dimension. And there is an exception that an exterior corner radius where the maximum radius is the minimum material condition and minimum radius is the maximum material condition. So this is a simple example. So if we are having a shaft or a pin, so there will be maximum material in this pin when this is made at the upper limit. So 10.1 is the upper limit and that is the maximum material condition, and in this case 9.9 is the lower limit and that is the least material condition. So there will be the minimum material in this part when it is made to the lower limit. In the case of a hole, when the hole is made smallest, there will be maximum material in this part. So the upper limit here is 10.1 and that is the least material condition. So when this hole is made at the upper limit, so we will be removing maximum material, so remaining material will be minimum. So that is the least material condition. And when the hole is made the smallest, that is at its lower limit, so that will be the maximum material condition in this case. So these concepts are central and we will use them to the design of fits as well as to the design of limit gauges. So the concept of limits, concept of tolerance, concept of two mating parts, and the concept of material condition. Thank you.